Let's solve another thermodynamic problem involving a closed system. This time, let's solve a problem that requires a rate energy balance. So we have a gearbox, and during steady state operation, this gearbox receives 60 kilowatts through the input shaft and delivers power to the output shaft. Convective heat transfer occurs from the gearbox surface to the surroundings as per the stated conditions, which we'll see here momentarily. For the gearbox as the system, evaluate the heat transfer rate and the power delivered through the output shaft, each in kilowatts. So you can see here that we have our system boundary drawn around the gearbox. Okay, so that entire gearbox is our system. And this input shaft delivers power to the gearbox. And it is doing a work, it's delivering energy into our system. So this power rate here is going to be negative, all right? And then we have an output shaft that delivers power from our system, so it's going to have a positive value. And also because there's some friction inside this gearbox, that friction will dissipate energy, and that will cause this to increase in temperature. And so the surface temperature of the box, T sub B, is going to be greater than the temperature of the air around it, and that will set up a case where we have convective heat transfer. So let's look at what that convective heat transfer looks like. Okay, now instead of having Q, we're going to have Q dot, and I can't actually type a Q with a dot over it, so I've shown it here as a Q prime, but we're going to call that Q dot. And whenever we have a dot over our Q or W, instead of just representing an amount of energy, it will be a rate of energy transfer. So Q dot will be energy per unit time, and W dot will be the same, energy per unit time. So the rate at which heat transfer is taking place here, it's the heat transfer coefficient, which here is given as 0.171 kilowatts per square meter per degree Kelvin, times the area of the box, which is given, the outer surface area is 1 square meter, times the different temperature difference between the box and the air. So we know that the temperature of the box is 300 degrees Kelvin, and the temperature of the air surrounding that is 293 degrees Kelvin. So that delta T is 7 degrees Kelvin, which is also 7 degrees centigrade. So let's go ahead and calculate the rate of heat transfer. And because our convention for Q or Q dot is positive when it's transferring energy via heat transfer into the box, in this case, because we're transferring energy out of the box, Q dot is going to be negative. So we've got our negative sign, then we've got our heat transfer our heat transfer coefficient, the area of the surface of the box, and the temperatures of the box and the air. And so we get that the rate of energy transfer is minus 1.2 kilowatts. So that means that Q is negative. It means that we're transferring energy out of the box via heat transfer. So now let's apply the first law in the form of a rate energy balance for this closed system. And remember that Q dot is the rate of heat transfer being a positive value for energy when it's transferred into the system. And W dot is the rate of energy transfer by work, a positive value for energy that is transferred out of the system. Those have been our conventions. So we can restate the closed system energy balance, which we had originally said was the change in energy during a process. It's just Q minus W. But we can put that in terms of rates. Instead of delta E, we had dE dt. The rate of change with energy with respect to time is equal to Q dot minus W dot. And if we're in a steady state operation, the EDT is 0 because the system is neither accumulating nor losing energy. So we can write a simplified energy rate balance for this closed system. We can say that the EDT is 0, and 0 is equal to Q dot minus W dot, or we could say that Q dot is equal to W dot. Now there are two work terms in this system. So this term here, W dot, in our rate equation, in our energy balance, is actually equal to W dot 1 plus W dot 2, where W dot 1 is the input shaft and W dot 2 is the output shaft. So what we have now, substituting this expanded definition of our work rate, we have 0 is equal to Q dot minus the work term, which is now W dot 1 plus W dot 2, or 0, if we remove our parentheses, is equal to Q dot minus W dot 1 minus W dot 2. Solving this now for our unknown, which is W dot 2, we get that W dot 2 is equal to Q dot minus W dot 1. Let's substitute known values. W dot 2, which is the rate of work being done by the output shaft, in other words, the output power, is equal to Q dot, which we calculated as a minus 1.2 kilowatts, minus the input power. But the input power is minus 60 kilowatts. And so we get that W dot 2 is equal to 58.8 kilowatts. And this should make sense. We have 60 kilowatts coming in and 60 kilowatts coming out, 58.8 coming out the output shaft and 1.2 coming out of our system via heat transfer.